All right, good morning, everybody. Make sure your ID's on your body. Make sure your phone is wrapped up and zipped up in your bag. I'm probably sedated about now, so this is your worst nightmare. It's me without me. Chapter 1, Section 3, Equations Review and Preview. We're going to go ripping pretty quick. If you need to have somebody pause the video and then, do that, that's fine. One of you guys can be in control of the play speed. That will work. But I do expect you to get the notes down. I will be checking your notes as well as your pre-reads when I return. Make sure you're checking the book, looking at the examples there. Make sure you're using YouTube to get more examples when we've gone too far, too fast, or you just feel like there's some more things you need to do. Let's get right into it. In example 1, we're talking about specifying variables, constants, and the domain of an expression. You'll notice down there I wrote, why is it not an equation? Think about that in your head. Most of you realize there's no equal sign, okay? So we're going to talk today more about this concept of domain and what it means, and we'll define it. And for a lot of things, it really doesn't make too much difference because this is a nice, simple polynomial expression. No equal sign, right? There's just a left side, not a right side. No comparison here. The English equivalent is my dog is just like a hanging phrase. There's no comparison. My dog is a German Shepherd. The left-hand expression, the right-hand expression is in the middle. Sentences, complete sentences are what equations represent in the mathematical language. Expressions are just ideas. They can take on many values. Remember that word value is different than the word variable. We understand that there are variables and constants. Those are clear to see. What is the domain? Well, it's the set of all real numbers that I can replace x with and still get a defined expression. Well, guess what? When you're multiplying, adding, subtracting, squaring, cubing, none of those things ever generate like the error message on your calculator. What does generate errors is division. When we've got division by x, we know that there's a possibility that you're going to get an error, and that's anytime x equals 0. If it's on the bottom, x cannot equal 0. If it's on the top, it can equal 0. And so when we talk about all the values that would leave you with a defined value from the expression, once you plug them in, we're talking about the domain. The trick to identifying domain in a lot of cases is identifying the restrictions. But there's nothing you can multiply by 3 and add 4 that would come up undefined. Therefore, all real numbers, the double line on the R is another way to say it, or we could say the interval from negative infinity all the way to infinity is the domain of this expression. Remember, the comma represents every single number and shaded part of the number line between those. Pretty straightforward, right? Well, until we get to something like this expression, which is not linear, it's rational. Remember that root word? Ratio, the comparison of two numerical values, division associated with that. If it's a rational expression, then we might end up with a domain issue, some things that are restricted. Most of you can spot the restrictions just by inspection, just by looking at it. Most of you realize that if I put t equals 1, 1 minus 1 is 0, 0 times whatever this is, which would be 4, gives you 0 in the denominator, and 1 over 0 is undefined. If you don't believe me, type the 1, hit the divided by, hit the 0. Use your fraction key on your calculator. Hit enter. You're going to get error as soon as you try. So 1 is a restricted value. Pardon me. Can you predict what the restriction is in this binomial? I hope you said -3, because -3 plus 3 is 0, and 0 times whatever would be 0, and we'd be talking about a denominator of 0 again. True? So when we talk about the domain of an expression, we identify what the restrictions are, -3, +1. You can do that with more complicated expressions by setting that denominator binomial equal to 0, move the 3, get t equals -3. Move the 1, get t equals 1. That way, if you get more complicated ideas, then you're going to be able to solve for whatever the restrictions are. Once you know what the restrictions are, t cannot equal -1, and t cannot equal, +1, and t cannot equal -3. Those two restrictions then will be stated as part of what's left for the domain. Variable is t, right? Constants are anything that's not a variable, right? The domain would be the set of all real numbers except those two restrictions, except 1 and -3. Okay? How would we write that? What would we say? Well, we could say that sentence, but I think a better way to state it, based on what we've been practicing, is thinking about the number line. Where does the number line start? Well, it starts at -infinity. Where does the number line end? +infinity. What's in between? All the real numbers. So every real number between -infinity and infinity. Do we have restrictions? Yes. T cannot equal, whoop, that's not what I was looking for. T cannot equal 1. T cannot equal -3. We have the equivalence of some holes. At -3, there's an open circle. At 1, there's an open circle. So to describe this, we're left with 3 intervals of the domain. Remember, they come in interval notation in order from left to right. You can never put a bracket on an infinity. You shouldn't bracket -3 because you're not allowed to use it except -3. You shouldn't put a bracket on 1 because you're not allowed to use it. So how would we write this in interval notation? Pretty straightforward. The commas are the shading. -infinity is the start of an interval. It ends at -3. What did we say about that stuff? We said, hey, it shrinks down, it rotates around, it becomes the comma between them, right? We should have parentheses, -infinity, comma, -3. We just described the first interval of domain and said exclude -3. Union, there's another interval in here that starts at -3 on the 3.0000 side and goes up to 1. We just took care of all those real numbers that are between them. Take that, rotate it around, shrink it down, it becomes a comma, right? Interval notation is basically a picture shrunk down to the 2 endpoints. Our last interval that we would state for the domain, what's the domain again? Oh yeah, it's all values of the t variable, in this case, that would leave the expression defined. 1 up to where? Oh, infinity, correct? So we go from 1 to infinity is all this yellow stuff. We went from -3 to 1, all that yellow stuff. Went from -3 infinity to -3, all the shading there. And now we have this statement of what the domain of this expression is. Every possible number between negative infinity to 3, but not negative 3. Every number between negative 3 and positive 1, but not 1 and not negative 3. And every number between 1 and infinity, but not infinity or positive 1. Any number in between there. And this is how we identify what the domain of that expression is. Why are we worried about it? Because it was rational, there was a ratio, there was fractions, and you can't divide by 0. Your turn. You might want to pause. I hope you got the variables. The variable was, that's right, x. Hope you got the constant. They happen to be coefficients on the variables, but the constants are 4 and 3. Is the domain all real numbers like the first example, or is the domain something different? I hope you said something different. I hope you said that term is 3 over x to the positive 1. And now we know that x cannot be 0. How do we know? We set the denominator equal to 0. Solve it. Well, it's already solved. And so all real numbers except 0, which means we go from negative infinity up to 0, union 0 to infinity. We've identified the domain of that rational expression. Okay? Pretty straightforward things, but you can certainly YouTube domains of expressions, domains of rational expressions, and watch some more examples on it. We better make sure we understand the difference between the expression and the equation. This is what we call a linear. Linear means first degree. First degree means all variables have the first power on them. Y to the first, x to the first, m to the first. Each of those variables has a first power, and therefore it is a linear equation in one variable. Wait, there are two variables. No, they're both y. That's what we mean by in one variable. All right? Why is this not a linear equation? Because this really belongs down here. And if it's down here, we know that its power is -1. We just moved it down there to get rid of it. This is a rational equation, not a linear equation. If it has any other power than 1, when it sits on the main numerator line, you know it's not a linear equation. Whether it's one variable or not, you count them up. Are there different variables? No, they're the same. Same thing if I had 4x plus 3x to the 1/2 equals 2. Not a linear because we're not first power. Same thing if I said 4x plus 3 radical x equals 2. Same statement, right? Looks like x is to the first power, but it's really not. It's to the 1/2 power. So make sure you can spot what a linear equation in one variable is. Next thing, if you're talking about equations, you're talking about solutions. Solutions are the value of the variable it plugs in and makes a statement true. It makes the left-hand expression have the same value as the right-hand expression. If I were here, we would play this solution definition over and over and over, and you would say it 100 times out loud in class. We would mix it up, remix it. We would do everything you could because this is the most important concept you can take out of this notion, because everything we do is dependent on the number of solutions. And what is a solution? It's a value of the variable that plugs in, say it with me, makes the statement true. It makes the left-hand expression have the same value as the right-hand expression, therefore producing a true statement. When I get back, I'm just going to play that thing like 20 times. You probably can't even hear it because of the microphone if I played it now. There are several kinds of equations in one variable. Equations that become true statements for all values of x. I don't care what you put in. Put in 33, 33, 2 times 33 plus 33. It's the same as 3 times 33, isn't it? So 33 makes this thing true. Put in 0. 0 plus 0 is 0. 3 times 0 is 0. 0 equals 0. It must be a solution because it made the left-hand expression have the same value as the right-hand expression. You can put in any number you want for x because these are equivalent expressions on the left and right. And therefore, no matter what number you put in for x, you'll get the same value out. What you think of as a normal equation are those that only have like one solution. Sometimes no solutions. Okay? Sometimes two, but not if they're a linear equation. So this is 3x equals 3. X must equal 1, correct? Divide both sides by 3. There is only one number that I can put in here and replace the x's and make the left hand have the same value as the right hand. Put in a 1, you get 2 plus 1, you get 3. 3 equals 3. The left hand value is 3. The right hand value is 3. They're the same. The solution is x equals 1. That's a big deal. You better understand what a solution is. Some of you think you know. I'm going to put it on the test. I'm going to ask, what's a solution? And you're going to say, it's the answer. And if it's a 10-point question, I will mark off 20. The solution is not the answer. So please don't ever give me that answer when I ask you a question like, what is a solution? You better give me the value of the variable that plugs in and makes a statement true. It makes the left-hand expression have the same value as the right-hand expression. You probably want to make sure you get that down, if not in the book, and I will test you on it. You're welcome. There's 3 points for you. I just told you what I'm going to test you on. Let's solve a linear equation in one variable, and let's start with something, that is not just 3x equals 3. Let's work on this thing. As you work on it, the first thing you should be doing is simplifying the left-hand expression. I will not do anything to move things to the other side until this expression is as simplified as it can get. Therefore, there'll be no changing of signs. There'll be no flipping of symbols. They'll just be PEMDAS. I'll take the negative 2. There's nothing inside the parentheses. I'll get negative 2x. As I distribute, I get negative 2. Outside of that, I have this bracket and the 1. So I just eliminated the parentheses. There's still a 3 outside. In here, I have 1 and negative 2, which are like terms. I'll combine them, and I'll get negative 1. 2x minus 1 is what's inside the bracket. There's nothing else that can be combined. Then I will distribute the 3 from out front. As I distribute the 3 from out front, I get 6x minus 3. The left-hand side has been simplified. I should look now at the right-hand side. Can anything be simplified? Not really. I could factor out a negative 1, but that's no more simple than the other one was. So I will now work on declaring which side is the variable side and which side is the constant side. And this is very much like that inequality up there on the board. I just looked over my shoulder, saw it up there. The 1 is less than 8, right? There was a matter of perspective. And the left side of the room said one thing and the right side of the room said something else. You all agreed you were saying the same thing. Perspective here. There are choices. There are decisions. Do you want to move the 6x over to the right-hand expression? Do you want to move the negative x over to the left-hand expression? That's your choice. My habit is to move the one with the smallest, most leftward leaning towards negative infinity coefficient. That means negative 1 as a coefficient is smaller than 6. That's the term I'm going to move. We get all variables to one side. We get 7x minus 3 equals 2. And once we've decided that this side is where the variables are, this side better be where the numbers go, which means the constants have to move from the left side to the right side. We do that by adding their opposite. Sign changed. 2 plus 3 is 5. We divide by 7. We divide by 7. We get x equals 5 over 7. Or whatever that number I just scribbled is. Okay? Pretty straightforward, right? Should I be able to plug it back in and prove that it makes the left-hand expression the same value as the right-hand expression? Yes, I should. You ought to take out your 115 ES plus right now. You ought to envision those as an extra set of parentheses. You ought to type it exactly the way you see it and plug in the proposed solution that we came up with and make sure that 5 over 7, when you plug it in, makes the statement true. If it does, you've correctly solved it. Okay? Thanks for that ignore. I know nobody plugged it in, but hey, I'm just here to try and teach you. Oh, thank you. I see that. Good. I appreciate it. Solving equations equivalent to linear equations, these are a specific type. You'll notice we are supposed to assume A, B, and C are constants. A does not equal 0, because if we did, there wouldn't be a variable, and we'd just be left with whatever constant this is equal to whatever constant that is. These are called literal equations. Literal equations frequently have very few actual constants in them, and they have to define what variable you're solving for, because you could treat any of them as variables. So this one would have to say solve for x. And when it says solve for x, that means you got to get x on one side and non-x's on the other side of the equation. And you move them and you divide them and you do everything the same as we did in regular linear equations with numerical constants and coefficients. If x is what I'm solving for, and my equal sign is right here, then b is on the wrong side because it's a non-x. It's got to go. How does it go? It changes its sign. You subtract b, you subtract b. You end up with c, and you subtracted b from it, and so you have a binomial c minus b. It's equal to the monomial a times x, and your job is to get x on one side, non-x on the other side. You have to ask yourself, what's the a doing to the x? Oh yeah, the a is multiplying. Then you have to ask yourself, what do I do to undo it? You should clearly know you would be dividing. Because these two terms should be subtracted if they were numbers, before I do the division, if that was a 3 and that was a 5, we would get -2. We draw the division Venn long enough so that it groups them and says, yeah, subtract them first and then divide by a. And we get x equals c minus b over a. Could I distribute the a to both terms in division? Yeah. I could get x equals c over a minus b over a, and it would be equally legit. But it seems like those two are left to be subtracted, and they haven't been combined and simplified. So the preferred expression would be x equals the binomial c minus b, all divided by a. Okay. Let me see if there's another one floating around down here. Is there another one floating around down here? No. Is there another one floating around down here? Yes. I'll get there. We'll do another little literal equation in a minute. I think it's the next example or two. And at that point, we will be kind of keying your attention in on something that's really important. Right here, clearing fractions. Are there any restrictions in this equation? Some say zero. No. There's no place to make the denominator become zero. You're only replacing x in the numerator with values. So there are no restrictions from the domain. It's important when you see the Vinckelmann fraction bar that you start thinking, are there restricted values? In this case, there's none. You need the LCD for all three fractions. You are not changing any fractions to arrive at that LCD. The LCD, because 2 will divide into 4, means I don't have to worry about it. 4 times 5 is 20, because if I do 20, 2 will cancel into it because it was able to divide into 4. Once you identify the LCD, you multiply not just one term, not just the terms with the fractions, you multiply each and every term with the idea of 20 over 1. Most of the time, I fail to write over 1, but I make sure I get the 20 in the numerator, because a fraction times a fraction, you can cross-cancel in order to reduce it. And this is why we picked 20 out of our hats, because you get 5x. 5 goes into 20, leaves 4. You get 12x. And 2 goes into 20, you get 10. 10 times 3, which has a negative sign, gives you negative 30. At that point, you get 17x equals 30, negative 30. And you would divide both sides by 17. 17's prime, I shouldn't worry about reducing that expression because I know it doesn't go into negative 30. This is the solution. It's the value of the variable that plugs in right there and there. You're welcome to punch that in on your calculator and show that when you come up, the left-hand expression has the same value as the right-hand expression. We can extend that logic and use what we learned in Chapter B, but this time, when I look at these rational expressions making a rational equation, we realize that, hey, x cannot equal 0. No, x cannot equal negative 5. Bring the 5 over. Negative 5 plus 5 makes 0, so x cannot be negative 5. X cannot be positive 3. Okay? I better figure out what this one is, but usually these are a big, fat quadratic made up of those two factors. Are negative 3 and positive 5? Yeah, probably. Why positive 5? Because the middle term's got a positive 2. And so the same two restricted values show up when I factor that denominator. So far I have 1 over x plus 5 equaling 2 over x minus 3 plus 2x plus 2 over those two multiplied together. So factor, state your restrictions. Those are the first two steps. Then LCD. What would be LCD? Well, you need to identify the types of factors. Oh yeah, there's x plus 5s, there's x minus 3s, and there's, oh yeah, another x minus 3 and another x. So the only types of factors are x minus 3 and x plus 5. This expression right here multiplied out. So I don't have to multiply by anything else. I don't need to multiply by 2 of the x minus 3s, because in each term, none of them appear as a squared or a cubed or a fourth. So I only need first power x minus 3 and first power x plus 5. I will use those to multiply where? Oh, in the numerator. On how many terms? Oh yeah, all of them. That's the last time I'm going to write the over 1. Because you know they got to be in the numerator, and if you don't show a denominator, it's implied as numerator. So each and every term gets multiplied by the exact same expression. Whether it's a number, whether it's binomials, whether it's a trinomial, you can't do something different to different expressions and preserve the balance that is this equal side fulcrum. This side has to maintain the same value as that side. Are there reductidations? Sure, yeah, you can reduce out the x plus 5. That's 1 times x minus 3. You get x minus 3 equals. In this next one, is there? Yeah, there is. There's a binomial, x minus 3. And you get 2 times x plus 5. There's the 2. There's the x plus 5. And in the last term of this equation, the x minus 3, bye-bye. The x plus 5, au revoir. What do we end up with? 2x plus 2. Okay? Keep solving. We're going to simplify the right-hand expression, simplify the left-hand expression, start moving stuff to one side. I want to get this stuff out of our way for a moment. I'm hoping you're ahead of us. I'm hoping you're distributing while I talk. 2x plus 10 is the distribution there, plus 2x plus 2, 4x plus 12. I've simplified the most complicated side. 4x plus 12. What's it equal to? X minus 3. Once I've done that, I can start bargaining for variable side and non-variable side. I will be moving the smallest of the two coefficients, 1, not 4, and bringing the x over here. That'll leave me with negative 3. I'm subtracting it. It gives me 3x plus 12. At that point, variables are here, then numbers are got to go on the right side. We'll bring the 12 over. It's going to change from a positive 12 to a negative 12. You're going to get negative 15 equals 3x. You're going to divide to get rid of the 3, and you're going to get x equals negative 5. And then you're going to be like, yay, go me. I solved this equation. I'm the king of the math world. No. You might have forgotten. What'd you forget? Oh, let me make it a little bigger. X equals 5 that we just obtained by simplifying the original equation. It doesn't check. I can't plug it back in and make the statement true. I can't plug it back in and make the statement true because I can't plug it back in. It's restricted. It's one of the values we identified as restricted from the domain because it would make you divide 1 by 0. That dog won't hunt. By the way, it would also change one of the factors in this denominator to 0, multiply by another factor makes 0, and you'd be dividing by 2 things where there was a 0 in the denominator. That is not allowed. What is it called when that happens? It's called a what? Oh, it's called an extraneous solution. Okay? Be on the lookout for those. On the test, there will be that sucker answer of x equals negative 5. Anytime we multiply both sides of an equation by something that has a variable in it, we multiply by those binomials. Anytime that happens, it may. Does it say it will? No, it says it may introduce extraneous solutions. Therefore, always check the original equation for what we call candidates for solution. X minus 5 was a candidate for solution, but it lost the primaries. Extraneous. And therefore, this equation has no solutions. Did we do something wrong? No. We just have to be conscious that when we multiply both sides of an equation by an expression containing a variable, it may, not will, it might, it could possibly introduce extraneous solutions. Therefore, you always have to check in the original equation to see if the idea -5 equals x is actually a solution. It's not. It's extraneous. All right, good. Make sure you do more. I would probably look for solving rational equations with extraneous solutions on YouTube. And I would watch a bunch of those if I cared. Okay? Do you care? Clearly I care, or I wouldn't be sitting here recording a lesson for you to learn while I'm probably dying. I don't know. No, don't hope that. I'm not dying. It's just outpatient surgery. Come on. What is the restriction in this example? X cannot equal -2. How do you know? Oh, you set this equal to 0, you move the 2 over, you find out what you can't have that would make the denominator 0. It's -2. You can't divide by 0. I don't care what the numerator is. It would never give you 4 if you tried to divide by 0. Now that we've identified the restriction, when we get done, make sure we come back and see, is our solution the restriction? Do we have to throw it away and say it's extraneous? We'll see. I'm going to clear my fractions. I'm going to clear my fractions by multiplying both sides by x plus 2. You might recognize cross multiplying to solve a proportion, but I'd prefer you think about multiplying by x plus 2 and multiplying by x plus 2. And when I do that, I get 3 plus x equals 4. The x's are on this side, the 3 is going over there, and I get x equals 1. Minus 3, minus 3. I got 1, right? Is 1 the restriction? Say no. No. Okay, good. It's not restricted, then keep it. Can you plug 1 in and 1 in to get 3 plus 1, which is 4, over 1 plus 3? Whoa, wait a minute. Something went wrong. Pause it. If I didn't already have 38 minutes recorded, I'd stop and scrap it and start over, but there's 38 minutes, so I'm just going to erase your brain for a moment. The x plus 2, this is why we check, right? The x plus 2 canceled here. It didn't cancel here. Therefore, you'd have to distribute, wouldn't you, Howard? Yes, you would. I know you were trying to tell me that, but I wasn't listening because I'm sedated. Mind you, little gnomes, doesn't it? Never mind. You can look that up on YouTube. Minus the x minus the x. I'm going to move the smallest x. I'm going to move the 8 to the other side. Minus 8. Minus 8 and positive 3 gives me -5. Got my x's out of there. 4x minus x gives me a what? Oh, gives me a 3. 3x equals -5. I'm going to check and see if -5/3 certainly is not a restriction. I wonder if it works. Or do I have to pause again? Let's check. 3 plus, no, minus -5 over 3 divided by -5 over 3. Plug it in here. Add it to 2. Somebody find the big 1. I got him. Right there. Okay, and our denominator is 6, isn't it? because that's a 3. Oh, no, it's just 3. That 2 is in the numerator, correct? So I'm going to multiply everything by 3 to clear it out. 3 times 3 is 9. And 3 times 5 over 3 minus 5 gives me 4 in the numerator. Then do the denominator, I get negative 5. And 3 times 2 is 6. And I get 1 in the denominator. And what's 4 over 1? Oh, it's 4, isn't it? I plugged it in. I proved that this is the solution. X equals negative 5/3 because it's the value of the variable you plug in and make the statement true. 4 equals 4. You get the value of the left-hand expression, 4 over 1, is the same value as the right-hand expression. A solution. Pay attention when you solve rational equations. Make sure you're checking for restrictions. Make sure you're plugging your solution back, or your candidate for solution back in to tell, hey, hail to the chief. Da, 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 da. Oh, that was stars and stripes. But anyhow, this one won the election, didn't lose the primaries. It's all good. We'll continue. Still recording. That's good news. This is a rational expression. This is a whole number expression. They're in an equation. It's a literal equation because it's all letters and numbers. They want me to solve for x. And they just told me that the denominator binomial, it can't be 0. That's just stated for you. Okay? So now, how do I work the magic of clearing the fractions when there aren't any numbers? It's really not that hard. It'd be a good place to cross multiply. It'd be a good place to multiply both sides by cx plus d. This type of problem literally comes up about 7 times in our course. I'm telling you that now, so you will pay attention when I tell you what to pay attention to. Both of you who are still awake, yep, will be better off for it. Cx plus d is what I'm multiplying on both sides of the equation. It cancels out and leaves me with ax plus b, and the y distributes to cyx, because x is my variable, cy would be the coefficients, and dy when I distribute it to both terms. Like every other equation we've solved for, you're trying to get x on one side and non-x's on the other. I don't care which one you move. Do you want to move the ax? Do you want to move the cyx? I'm going to move the ax. Cyx minus ax, because they both have the variables I'm putting next to each other, plus dy equals b minus ax on both sides. All right? Hope that woke you up. I'm supposed to have x's on this side and no x, or the non-x's on this side. So I'm going to keep those two terms here as if I could add them up, and the one without the x is going to the other side. Cyx minus ax equals b. How do I move it? Oh yeah, minus dy and minus dy. And we get the binomial b minus dy. We've been going at it for almost 40 minutes of examples, 50 minutes of examples almost, and we're at the most important part of the lesson today. It's the part you're going to mess up when you start checking for a whole bunch of things if you don't pay attention. So wake up. Hello? All right. You got the x's on the same side? Factor out the GCF, or at least the CF of x. Now I have two terms with x, but in a moment, I have one binomial multiplied by x. Cy minus a. And if you want to, then you better, and you should pay attention, factor out the x. You got one x here. Guess what it's doing? It's distributing. It's multiplying. How do you undo multiplication and get the x by itself? Yep. You divide off the binomial. Oh, that was cy minus a. Cy minus a. And you get the expression that equals x. You get x equals b minus dy over cy minus a. If you got a multiple choice test, couldn't somebody have factored the numerator -1 out and the denominator -1 out? And wouldn't that switch the signs and change the orders? Couldn't you have negative dy minus b and negative a minus cy with the negatives canceled out? You could have had that, right? You could have had just the denominator factor out a negative sign, move it to the numerator, and distribute it in. There are many ways to look at this expression. Make sure you understand all of them when you're checking a multiple choice answer. Does that mean the next test is multiple choice? Maybe. Maybe not. The last bits of the examples that are here in this lovely, almost hour-long lecture on giving examples and definitions from equations review and preview are quadratic equations. Gosh, I hope by the time you get here, you know what they are. Gosh, I hope you know they have to be in standard form. Ax squared plus bx plus c equals 0, because it's not a quadratic expression. That is, no, it's a quadratic what? Equation. Equals right side, left side. Therefore, our solutions must make the left side have the same value as the right hand side. And therefore, when we plug them in, they'll make the statement true. So they better make this expression equal to 0. That's why we call them zeros, roots, x-intercepts, etc. Because they're all associated with the same idea. The zero product property of real numbers says you know something about two things that multiply and give you 0. Either P was 0 or Q was 0, because you can't multiply P times Q and get 0 any other way. That's why we set things equal to 0, so that we can create multiplication. Oh yeah, what do we do? Factoring on multiplying creates a multiplication problem out of an answer. And so we could set those two equal to 0 and test and see. Oh, that means this is probably factorable, because P times Q must be two factors, things that are multiplying. Oh yeah, good, I'm good at this. AC. It's negative 24, isn't it? Are there things that multiply to make negative 24 that add up to be negative 10? They had to be different signs, so think subtraction. 12-2 comes to mind as I Jedi it. Made a little mental list of the 1, 2, 3, 4, 5. Right? 12 and 2. I want the 12 to be negative. I want the 2 to be positive. And I want my over 8s on both binomials. My magic numbers must be negative 12 and positive 2. And we're going to set each factor equal to 0. after we get the true factors. We deducted 8, pardon me. Take 4 out, we get 2. Take 4 out, we get 3. You could think of it as 4x minus 3, but that would be crazy. Because you're going to move the 3 and divide by 4, which is 3 over 4. We're foreshadowing there with my 4s. 2 goes in, leaves a 1. 2 goes in, leaves a 4. You could write 4x plus 1, couldn't you? You go ahead and FOIL that out. You're going to get negative 3. Positive 8. Yeah. But I wouldn't. I would just leave this, not the real factor, but and it says, hey, if 2 things are multiplying and they equal 0, then either what? Oh, the first one is 0, or the second one is 0, or both of them are 0. So let's maximize what we know. Set the first one equal to 0. We're going to get x equals positive 3/4. Put the second one equal to 0. You're going to get x equals negative 1/4. Was there any division up here? No. Is it rational? No. Is there anything that you couldn't square and be defined? No. The domain of this expression is all real numbers, and so I don't need to worry about expressions or extraneous solutions that come from rational ideas with a denominator expression, etc. Did I multiply both sides of an equation by a variable? No. I don't even have to worry about extraneous solutions at all. These dogs will hunt. Those should be the solutions. Plug them in with your calculator, test it out. Did I miss a number 2 or 3 or 4? I got the 2. Did I take that? Just checking here. 4 went into 8, not 4 times. 4 went into 8. How many times? It's getting late. I should probably just, wake up from the anesthesia right about now. How many times does 4 go into 8? It goes into 8 2 times. And here it goes 3 times. That should be a 2. That should be a 2. It should be 3 halves. That means it's 2x minus 3 and not 4x minus 3. My apologies. You can try that on a test. It doesn't help. I'm sorry, too. But you set each factor equal to 0. You solve. You get x equals 3 halves. You get x equals negative 1/4. With that, there's only one last thing we need to do. Solving by factoring the quadratics. And after that, yeah, you guessed it, the quadratic formula. Do you need to have it memorized? Yes. Does your calculator do mode 5, 3? Plug in 1, -2, -4, and get the exact simplified values from the quadratic equation? Yeah, great way to check it. Mode 5, 3. You'll plug in the A, the B, the C, hit equals, hit it again for the second root. Then you can hit it again and get the vertex X, and hit it again and get the vertex Y. And we're not to that yet. We're simply right here, right now, using the quadratic formula. In standard form, it has to start that way. AX squared plus BX plus C equals 0, where A is 1 here, B is -2, and C is -4. Get ready. Plug them in. B is -2. A was +1. C was -4. And most people screw this term up if they're going to do any screwing up of the quadratic formula. We hope that's not you. Calculate that term first. Count the negative signs first. Two negatives make a positive. Then work out its numerical value of 16. Then square the negative 2 for 4. Then look at the square root of 20 and think, gee, 4 times 5 is 20. The square root of 4 and the square root of 5 is 2 radical 5. Now that I've got the radical simplified, I better put my plus, minus, because that radical was there. We didn't bring it. And change the sign of my b out front. The opposite of negative 2 is positive 2. Positive 2. And the denominator is all over 2a. What was my a? 1. I might have forgot to plug that in a minute. 2a. My a was 1. So my denominator is all over 2. I hope you've met the clown. I hope you remember the clown. I hope when you're down, you'll think of the clown and ask yourself, self, does it factor and cancel? We'll check both eyes and the nose. If both eyes and the nose have a common factor, take it out because there's 1, 2, 3 terms. It's like dividing everything by the same number. If I take out the 2, I get 1. If I take out the 2, I just get plus or minus radical 5. If I take out the 2, I get over 1, and nobody would write. Wow. Nobody would write over 1 because that's overdone. So we would get rid of the over 1. And we would say there are 2 irrational. That's the clown's ear. It's not a very good one. Irrational solutions. 1 plus the square root of 5, which, by the way, you want to see a million digits of it? No, I didn't think so. And 1 minus the square root of 5. This is an irrational quadratic solution. It's irrational that I'm still here at 6:20 in the evening working on recording your lesson. And who knows if anybody is still awake at this point. But let's hope so. Make sure you take care of the 1.3 homework. You wrote it down. I believe it's 1 through 51 odd plus 63 and 65. Make sure you pre-read section 1-4. I would do some more pre-reads this weekend to lighten your load during the week. And if you need to see more quadratic equations solved with the quadratic formula, YouTube. If you need to see more solving by factoring on quadratic equations, YouTube. If you, and you definitely should, look for more examples of literal, rational equations. Literal. All letters and not very many numbers. Rational. Fraction on the bottom with the variable equations. I would YouTube that as well. So hope I don't die. I hope you have a great weekend. And I hope that 1 hour will leave you about 30 minutes to get crack-a-lacking on that homework assignment. I do not want you to sit here and chit-chat for the rest of the hour and waste your time. Do another pre-read if you've already got the homework done. Work on some other homework quietly. And put your phones away, for goodness sake. They should be wrapped up and zipped up in a bag. I know, you're chuckling now because you see them. All right? I will catch you as soon as they let me catch you, assuming that all things go well today. All right? Have a great weekend.